Okay, good day class. So we will continue with the topic of Laplace transforms and its inverse and how is it used in determining the solution of higher order differential equations, whether homogeneous or non-homogeneous, but having constant coefficients. So the first two properties talk about the Laplace transform being linear, and correspondingly that also is true for its inverse Laplace transform. With Laplace transform being linear, it allows us to evaluate piece by piece a given expression of a function of t, meaning we evaluate the Laplace transform of each of the terms separately. Now, when you speak of linearity of the inverse Laplace transform, which is the second property, we do the same. It should be possible for us to invert the terms of a function of s by converting it into a form that is recognizable in terms of what is provided in the table as to the Laplace transform of the basic functions of t. So we should set aside for both Laplace transform and inverse Laplace transforms the constants that appear with our function of t and our function of s, and later on, after we're done with Laplace transform and inverse Laplace transform, we multiply our answer to those constants that we have set aside. So moving on, we will continue with the third and the fourth property of Laplace, which is actually the real meat of the topic of Laplace transform. I say it's the real meat. If you're eating a meal, this is the main course because it tells you how you are to evaluate or determine the solution of higher order differential equations using Laplace without having to recall the techniques that have been discussed since prelim. So this time you are to forget all of those, and even the topic that we have discussed on higher order homogeneous and non-homogeneous differential equations, because we're not solving our differential equation based on those techniques, but rather we're using the method of Laplace. So property number 3 allows you to get the Laplace transform of a derivative of a function. So if you will get the Laplace transform of the derivative of a function, so the function can be x, could be y, could be any variable or any letter, that would entail you to multiply the function of s of that particular function with s and then subtract the f of 0 for that. So if this function is y, so this is s y of s minus y of 0. The reason why you see a plus sign on the 0 here is that the function is approached from the right side of the Cartesian plane up to the value of the t, in this case the t, the independent variable, being equal to 0. We don't approach this value of 0 for our independent variable from the left side because our Laplace transform of t does not have any meaning for time or for t, which is negative. So it has to be approached, the value 0 for our t should be approached from the right side. Now, this is Laplace transform of derivative. So this is just the first derivative. If it's the second derivative, the same pattern will be followed through. That would be discussed in the next slide. So the fourth property of Laplace allows you also to get the Laplace transform of the integral of the said function. The limitation of this Laplace transform of integral is only for integrals, for definite integrals, which has limits 0 to t. If the limit of your integral is not from 0 to t, then you cannot use Laplace transform or you cannot evaluate the Laplace transform of your given integral. What does this particular formula tell you? Whatever is the function that you see written after the integral sign, you are to transform it based on the formulas that were given in the table, and all you have to do is divide it by s. This is true for all functions of t's, which can be transformable as long as the limit of your integral here is from 0 to t. If this is negative t to t, this cannot be done. So there's no Laplace transform of such a particular integral. So using these two Laplace transform properties together with the inverse Laplace transform property, we will now learn how to determine the solution of higher order differential equations with constant coefficients, meaning homogeneous or non-homogeneous maybe, using this particular property, specifically property number 3. Now, we have learned that the Laplace transform of the first derivative is s times the function of s minus f of 0. If it's the second derivative class, the exponent of the s here, which is originally 1, now becomes 2. It's because the s here is raised to the order of the given derivative. We multiply the function of s, the function of 0, and the derivative of the function evaluated at 0, as long as we still have an s here in our terms. Meaning, you start with s squared, then you subtract 1, that would be s, and then you subtract 1, that would be s raised to 0, which is 1. That tells you that you are now to end writing the derivative or writing the Laplace transform of your derivative because you already ended with an s raised to 0. It's the same thing here. It's s times the function of s minus, so if this is s minus 1, if you subtract 1 from the 1 exponent of the s, that would be s raised to 0, and that would be this. And now then, that tells you that this is the last term in the derivative or in the Laplace transform of your given derivative. The way you do the term that you are to multiply on the decreased exponent of the s is this. This is really true. The pattern is you start with f of s, then you go to f of 0, then you go to f prime of 0. If there's still an s that appears, then you should end with an s double prime of 0. So all functions and its derivatives here are all evaluated at 0. Now, it's s squared, it's s, then raised to 1, and s raised to 0. If this is s cubed, this should be s cubed, s squared, s, and you should have another term here, which is f double prime of 0 already. So, we increase the order of the derivative as we go to the last term that appears in the solution of our Laplace transform of the derivative. We start with f of s, the Laplace transform of the given function. Then we follow with f of 0. Then now we follow with the derivatives of the function evaluated at 0. We end when there's no more s multiplier, just like this one. There's no term after this because this term does not anymore contain the s, or it's understood to be s raised to 0. The Laplace transform of the integral of a function evaluated from 0 to t is simply to be viewed as the Laplace transform of the function of t here, written after the integral, and that's your function of s here, and you automatically divide it by s. That's just how simple property number 4 is. But this one is really detailed in terms of its application in the solution of higher order differential equations. Now, determining the solution of a higher order differential equation, whether homogeneous or non-homogeneous, using Laplace transform follows these 4 steps. So the step 1 or the first step is to take the Laplace transform of your given equation. You take the Laplace transform of the derivatives and you take the Laplace transform of the functions if there are functions appearing on the right side of your differential equation. After that, you convert your given equation into the form n of s over d of s. What does this imply? You will set aside one side of your equation to y of s, and the rest of the terms that is not y of s or that does not contain y of s should be written on the other side, and it will result to this expression. The n here simply means numerator, the d here means denominator, telling you that both the numerator and the denominator of this expression is a function of s. The third step is for you to ensure that the d of s, the denominator, is in factored form. That way you can perform partial fractions or partial fraction expansion, of course, with the determination of the undetermined coefficients. Then you will have to end with the step in which, after you have determined the coefficients of your partial fractions, you are now ready to invert the equivalent partial fractions using what you have in the given table. okay, in the table that was shown to you in this slide. So it will be illustrated using the following examples, this particular 4-step procedure. Okay, now in this example, you're given a first derivative of y with respect to t plus 2y being equal to 12. Now, you will have to take, the first step is you take the Laplace transform of each of these terms. So, that would mean that the Laplace transform of dy dt, this one, is actually written here. Okay? The Laplace transform of 2y is now 2 Laplace of y. And the Laplace transform of 12, this one, is this. So, you take the Laplace transform of each of your terms in your given differential equation. Now, what will happen after that? You will have to apply the formula for Laplace transform for the derivative for this one. And you will have to perform Laplace transform of simply y. What does this mean? So, if you will substitute the formula for the Laplace transform of dy dt, that would be s, y of s, because this is the first derivative, minus y of 0. But what is y of 0? Your y of 0 is 10. So, that is why you see here at 10. Actually, this one is your y of 0. Now, it's because of this formula that you see here. S, y of s minus y of 0. So, I just changed the f to y in here. So, you apply the same pattern or principle here. The Laplace transform of 2 Laplace y is 2y of s. Like, the Laplace of y is y of s. The Laplace of x is x of s. The Laplace of any t, of any letter for that matter, will be that letter. Then you just simply express it in terms of the function s. The Laplace of 12, which is a constant, is 12 over s. Now, you have to, in this case, class, you have to isolate the terms, or you have to factor out the terms which has y of 8, and you will keep them on this side of the equation. You see this? The terms which has the y of s, you keep in the side, so that would entail y of s being multiplied to s in this case, and plus 2 in this case. The term that does not contain the y of s, you transfer on the other side. So, this one, the 10, you see here. So, if negative 10 is transferred, if transferred on the right side, would be positive 10, or that would be plus 10. Now, you need to, based on step number 2, you need to isolate the y of s in this side. So, that's the step 2. I'd like to go back to that. So, you see this? You have to isolate now the y of s on one side, and the rest should be written on the right side, and the resulting expression would be a rational expression. So, if you do that, that would entail that this entire expression here will be divided by s plus 2. That way, now you have isolated already your y of s. So, this is now your y of s. You have isolated it, and now the 10 here will be divided by s plus 2, and the 12 over s will be divided by s plus 2 as well. So, you divided the entire equation by quantity s plus 2. In that same note, now you have already produced two fractions or rational expression. This one is readily invertible because your 10 over s plus 2 would simply yield an exponential function. A 10 which you can simply set aside and you place 1 in the numerator. But for the second term, this is where you're going to apply method of partial fractions because you have now two linear factors, the s and the quantity s plus 2. And I think you know in your integral calculus and even in the previous topic on method of undetermined coefficients on how you need to process this expression here. So, we only process the 12 over s times s plus 2 because the other one is readily invertible. So, if you do that, this will be your equivalent partial fractions. Now, after that, you determine the values of the two coefficients in whatever method that you choose to. So, you can set s equal to 0 or you can set s equal to negative 2. That would make these two denominators one at a time equal to 0. Now, the corresponding answer for the coefficients We call this the undetermined coefficients. In the method of undetermined coefficients, the resulting value for the constant a1 and a2 would be 6 and negative 6 respectively. Now, then your partial fractions written here, the 10 over s plus 2, and this one, which has two equivalent partial fractions, will now be looking like this. A 10 over s plus 2 plus 6, since a1 is 6, so 6 over s, and negative 6 for the a2. Now, this has the same denominator, right? So, you can combine these two. You can combine these two. A 10 minus 6, that would be a 4 with one denominator. If you will invert, this 6 over s is actually telling you that you have a Laplace transform of a constant, because the Laplace transform of 1 is 1 over s. So you simply set aside the 6 here and process the inverse Laplace transform of 1 over s, and that would simply be 1. 6 times 1, that would be 6. Well, this one, you can readily set aside the 4 here, and if your denominator is s plus 2, that tells you that it came from the Laplace transform of an exponential function. The numerator of such Laplace transform is simply 1. So you just simply get the Laplace transform of 1 over s plus 2, which is e raised to negative 2t, and multiply the constant 4, which you have set aside. So this one is already the Laplace transform, or rather, specifically not just the Laplace transform, but it is actually the inverse Laplace transform of this entire equation. The y of s, when you invert it, will be y of t. This one, when combined, would be 4 over s plus 2. If you invert it, that would be 4 e raised to minus 2t. And your 6 over s, if inverted, is 6. Now, class, the answer y of t, which we have here, this one, that's the solution of the given first order differential equation. That's the solution of this differential equation using Laplace transform. Actually, you can do separation of variables for that, or you can have it treated as linear, but the thing is, now you have an alternative procedure in determining the solution of that first order differential equation. So that's how you use the method of partial fractions and the Laplace transforms of derivatives. So let's go to the next example. This time, let's say we keep what we have in the original example. It's still dy dt plus 2y, but we will change what we have on the right side to be 12 sine of 4t. So naturally, the Laplace transform of this will be the same as the previous example. Sy of s minus y of 0, which is 10, and 2y of s for this one, the Laplace transform of 2y, and this one will only entail initially the Laplace transform of sine 4t. So the Laplace transform of a sine function is the omega, or the constant that appears in the argument of your sine, this case 4, and that would be s squared plus omega squared, which is 16. The set aside constant will simply be multiplied to what you have here, which is 4. So now, you have 48 over s squared plus 16. Just like what you did in the previous example, you transfer this 10 on the other side, and you keep this y of s, the two terms which has y of s, in this side. So actually, what happens is, if you factor out y of s on this side, you will have s plus 2 as their common factor, just like in the first example. So you have s plus 2 here. So what you will do with the s plus 2 is you distribute it as, actually you only have one term here on the right. So you will distribute this s plus 2 on this term, so that you have now s plus 2 times s squared plus 16 for this fraction, plus the fraction resulting from the 10 which you need to transfer here. So 10 divided by s plus 2 coming from this s plus 2 when you factor out y of s. Now, if you look very closely, again, this one is invertible. We don't have any problem with this. But this one results too. So, look at it very carefully. This one is a linear factor. and this one is a quadratic factor. So when you recall what you've learned in integral calculus and method of partial fractions, even in the method of undetermined coefficients in our subject, just in this n term, this constitute a linear factor and a quadratic factor. If you have a quadratic factor, the representation of its partial fraction equivalent will have two terms in the numerator. One undetermined coefficient with an s and another one which does not have an s. So this is b sub 1s plus b sub 2, or if you recall our presentation in method of partial fractions, I would write this as bs plus c. In this case, I just changed the b and the c to b sub 1 and b sub 2, but it's exactly treated in the same way we treated this partial fraction which has a quadratic factor, just like we have treated it in the method of undetermined coefficients. This one is readily invertible. We don't have any problem with this, so this one will need the method of partial fraction if you want to. However, class, if you could see, this is readily, shall I say, invertible as long as we know already the undetermined coefficients or the constants b sub 1 and b sub 2. And since we still do not know the 2 and even a, we need to use the method of partial fractions. So if you use the method of partial fractions, in the case of this one, the quadratic factor, because the first one is just linear. So this is our quadratic factor. This is it. This is it. This would be the resulting expression. So you have 40, the A would be 2.4, and your B1 and B2 will be negative 2.4 and 4.8 respectively. Now you have written B1 and B2 here. If you have already B1 and B2, I will leave the procedure and how it's being determined. Then you can have this partial fractions evaluated. This one stands alone, while this one needs to be separated. So the s over s squared plus 16 will be inverted separately from this constant over s squared plus 16. So this is how it's going to look like. So n plus s plus 2.4 s plus 2 minus 2.4 s over s squared plus 16 plus 4.8 s squared plus 16. So these are your corresponding y of s on the right side of your differential equation. This one stands alone. This one stands alone. We did not do anything about this. But the 2.4 that we have here, because you still have an s plus 2 here, that's a linear, and this one is a quadratic factor. We expect that we should have 3 more partial fractions for this, even if this one is set aside. So the corresponding partial fractions, the 3 more are these 3. Okay? Coming from the second fraction. Then you can have it inverted. So this s plus 2 tells you that's an e raised to negative 2t. And this 10 and this 2.4 were added. So we just added 2. So that would be 12.4 because they have the same denominator. These two have the same denominator. However, this one has an s and this one has a constant. So as for the s, that's automatically a cosine of the square root of 16, which is 4t. And you just copy the 2.4. In the case of the 16 here, the square root is 4. So this 4 should be placed in here. The 4.8, since you introduce a 4 in here, you will introduce a 4 in here. The 4.8 should be divided by 4. So that results to a 1.2. Sine of 4t. So this expression, y of t being equal to 12.4 e raised to negative 2t minus 2.4 cosine 4t plus 1.2 sine 4t is the solution of the given differential equation using Laplace transformation. Now, in the case of this particular sample 11, so the first two I gave you are all first order. So let's try something which is higher ordered because it's actually the main application of Laplace transform. So this is second order. This is second order. You could see it's second order. So we expect that we will start with s squared y of s. Then we should have an s y of 0. Then we have y prime of 0. Your s y of 0 is automatically 0 because your y of 0 is 0. So you see this? That's it. Whereas your y prime of 0 after the sy of 0 is 10. So this is your 10. If you take the Laplace transform of 2 dy dt, that would be 2 sy of s minus y of 0, because after y of s is y of 0. Y of 0 being 0, so you simply have sy of s. As for the Laplace transform of 5y, that would be 5y of s. So just like in the first example, getting the Laplace transform of y yields a y of s. If it's an x, that would yield an x of s. Any letter for that matter, as long as it's in terms of s when you perform its Laplace transform. The 20, when transformed, will be 20 over s. Now again, just like what we have done in the first two procedure, you need to, I like to change the color, you need to set aside the terms which has the y of s. So this one has y of s and this one. Okay? If you factor out the y of s in these three terms, your first term will be an s squared. For this one, s squared plus a 2s. So you see here, this is an s squared and a 2s. And this one, which is a 5. So this is the 5 that you are seeing here. The 10 was transferred here on the other side. So this is plus. So you have your 10 here. And that 10 will be divided by the factor which I have mentioned. S squared plus 2s plus, s squared plus 2s plus 5. Okay, so that's it. This is the divisor. The 10 was divided by this, and so you have this. The 20 over s was further divided by s squared plus 2s plus 5. Now these two have to use method of partial fraction. You may combine them into one fraction, or you may separately process this from a different partial fraction and this one also. It depends on you. But if I may suggest, you need to convert this into one fraction. That way, you only need to perform method of partial fractions once. Okay? Now, the 20 over s times the quantity s squared plus 2s plus 5 will result to an a over s plus bs plus c over s squared plus 2s plus 5. You have a linear factor here, partial fraction, and you have a quadratic factor, partial fraction. If you do the necessary procedure of finding the value of the undetermined coefficients, like you can equate coefficients or you can assign values for x, the corresponding value of a and b, if this is already known to be 4, is negative 4 and negative 8. Telling you that your second term will now have your y of s will now have 4 over s. Let me see. So you will have 4 over s and these two, negative 4 plus negative 8. So that would be this one over this, plus the other one which did not undergo any partial fraction. Why did it not undergo partial fraction? Because it's only quadratic in nature. So if you will combine a negative 4s minus s plus 10, it would be a negative 4s plus 2. Because anyway, they have the same denominator. So we combine the two into one, these two into one fraction. This is the fraction equivalent. So you will have now s squared plus 2s plus 5 being equal to s squared plus 2s plus 1 plus 5 minus 1. By the way, class, this one is just a procedure on how you're supposed to shall I say, have this inverted. So if you notice here, class, if you will already have this inverted, it is already invertible. What do I mean? Even if you don't think about this, that's written here, that only shows to you the shall I say, the method of completing the square, which I have discussed already, these two are already invertible. Okay, the 4 over s is invertible, and this one will be written with the same shifting as reflected in the denominator. So your s squared plus 2s plus 5 is equivalent to the quantity s plus 1 squared plus 2 squared. If you have this expanded, you will have this. So now, the reason why you have it written like this is for you to convert your original expression into an invertible form, wherein it could be readily inverted, or you can readily find the function of t after inversion. Now, since your denominator here has a shifting of s plus 1, you have no choice but to reflect the same shifting here in the numerator. So now your numerator is negative 4s minus 4. But your original is only 2. So what will you add to minus 4 to make it a 2? That would be a 6. So you could see this is 6. The 6 was factored out into 3 plus 2 because we want this only to appear standard as the inversion of the sine function, resulting to a sine function. If it's a sine function, the constant that should be written in the numerator is the omega in the sine. This is it. That's the constant here. So your 6 has to be written in the factored form wherein you have a 3 and a 2. Now these two, the last two terms, this one is anyway 4 in terms of its inverse Laplace transform. The last two terms yields a Laplace transform of a shifted. There's a shifting that happened to the cosine and the sine. Why do we say that there's a shifting? Because the standard s in the formula was changed to s plus whatever is the constant that appears here in the argument of your exponential function. This is the solution of the DE class, the second order DE using Laplace transformation. Now moving on, we have this last example, and this one is even higher in order. So this is a third order DE. Now it comes with the initial condition that y of 0, y prime of 0, y double prime of 0 are all zeros. Y prime of 0 is the value of the first derivative when you set time is 0. Y double prime of 0 is the value of the second derivative when you set t equal to 0. So this is how you should interpret this. Your y of 0 is the value of the y, the unknown function itself, when t is set to 0. All of this is 0. Now, you see this du dt. This is your du dt here. This is your, shall I say, this is your unit step function. The u, or rather not the unit step function, but rather, shall I say, another variable. U is another variable here which you need to invert. So it says here that since you need to invert this one, your du dt, the derivative of the unknown function u with respect to t is 0 at t equal to 0. When you take Laplace transform, this one, since everything is 0, will be only left with s cubed y of s. Because your s squared y of s, your s y prime of 0, and your y double prime of 0 will all be 0 because of this. Okay, this will all be, this one, if expanded, would simply be this. I'm referring to this one. If you will invert the the second derivative of y with respect to t, the same thing. It would be s squared y of s minus s y of 0 minus y prime of 0. Again, it's 0. So this one is just 6s squared y of s. This will be s y of s minus y of 0, which is also 0. So that leaves you with 11s y of s. The Laplace transform of 6y is just 6y of s. The Laplace transform of the derivative of u, first derivative of u with respect to t, is su of s minus su of 0. Again, it says here, du dt is equal to 0 when t is equal to 0. So meaning, it would also be 0 for this one. that leaves you with the Laplace transform of 4 du dt being just equal to 4s y u of s. Because the next thing to this, the u of 0 would simply be a 0. Okay, this one, it's 2 u of s. Okay, u of 0 being equal to, or that would be the derivative of your unknown function being equal to 0. Now, if you will factor the y of s here, this will be the resulting expression. That's your resulting expression. And you have in here, if you will factor the u of s, this will be the, I'll change the color. If you factor out the u of s here and the u of s, you will have 4s plus 2. Okay? So this one resulted from the factorization of y of s from this side. So this is it. And this one resulted from the factorization of u of s here. So that would be 4s plus 1. Now, where is this particular, I'll just change. Where is this particular 1 of s came from? Where did it came from? So I'd like to go back to the table which I have shown to you at the start of the topic. It's actually a function that you will encounter in controls, and I have partly introduced it here to you. You can see this is the u of s. The u of t has a Laplace transform of 1 over s. So meaning, I like to go back to that. The u of t, or the unit step function, has a Laplace transform of 1 over s. That 1 over s is the one that you saw here. This u of s class, if represented in terms of a representation, the unit step function, or the Laplace of the unit step function, it's 1 over s. So we replaced u of s by 1 over s. As defined here, u of s is 1 over s, the unit step input. Now, this would be one very long process of inversion, because this is already 4th degree, right, in s. So expect that you should have 4 undetermined coefficients, meaning you will also have 4 partial fractions for this. So if you will factor your denominator, this one, the resulting factors will be s plus 1, s plus 2, and s plus t. Good, because they are all linear. So you can set values for s in which a particular set of terms will be set to 0. Okay, you know that already. So the undetermined coefficients that you need to determine here is alpha 1, alpha 2, alpha 3, and alpha 4. Alpha 1 is 1/3. Alpha 2 is 1, alpha 3 is -3, and alpha 4 is 5 over 3. When you have the constants written in the numerator of the partial fraction equivalent of our original function of s, you would see that they are readily invertible. So this is a constant, this is an exponential function, this one is another exponential function, same thing with this. They only differ in the constants in which these exponential functions are multiplied to, and their arguments. So they have different arguments. Now, this is the solution of that differential equation, having y and the unit step function as functions related in just one differential equation. Now, to be able to introduce the last two properties, you see this t approaching infinity. In controls class, this is referred to as the ultimate value of your function. It's just like the t here will be replaced by infinity. Same thing with this, and this. In processes, it's referred to as the value after a very long time. Or we could call that the ultimate value or the final value. So if you will substitute infinity here, the ultimate value is 1/3. So we say that's the ultimate value, or that's the final value, or that's the value after a very long time. Now, how do we determine the final value of the function, even the initial value of the function, without having to resort to this very long process of inversion? What does that mean? Is there another way of determining the final value of the function without you having to invert a very long differential equation, just like the sample problem number 12? The answer is, of course, yes. And that brings about the last two properties that I will be discussing here for Laplace transformation, and that's the initial value theorem and the final value theorem. The initial value of the function is the value of y of t, or the value of that function when the independent variable is set to 0. Meaning, if you have inverted already the function of s, and you already have the corresponding y of x or y of t. If x is your independent variable, then it's y of x. If it's t, then that's y of t. You have to substitute 0 to those t's, and then you will know the initial value of the function. As for the final value of the function, just like in the previous example, you will substitute infinity to all the t's that you see in that particular expression for the y of t or for the y of x. Now, let's say if you're going to ask, can we have a different procedure wherein we don't need to do inversion? The answer is here. So, property 5 and 6. Without inversion, the initial value of the function is simply the function of s of that function. No need to invert the original function of s. You simply multiply it by s. And then the resulting expression you evaluate as s approaches infinity. Meaning, you substitute infinity for all the s that appears. If your corresponding expression result to an indeterminate form, what's an example of an indeterminate form? Like in your differential calculus, infinity over infinity is an indeterminate form. You will have to use L'Hopital's rule, or the techniques that you have learned in calculus, how to convert an indeterminate form to something which is specific in value. And that is in the case of the initial value theorem. The formula for the initial value theorem and the final value theorem are actually very similar. They only differ to the value in which s is approaching to. For the final value theorem, you need to substitute 0 for the s in the product of s times the function of s. In the initial value, it should be infinity. Now, but you have to, I'd like to emphasize this class because this will appear again in controls. But you have to remember that the final value theorem, unlike the initial value theorem, has a limitation. If the value of s times the function of s is infinity for real values of s greater than 0, this particular formula cannot be used. So, let's say, for example, you have your function of s. You multiply it with s. Then, you substitute, for all the s in that product of s times function of s, a value that is greater than 0. If the resulting expression assessed here is infinity, your formula for the final value theorem will not be applicable anymore. You have no choice, but you really have to invert the given function of s and substitute infinity to all the t's. But if there's no worry about the product of s times the function of s being infinity for real values of s greater than 0, then you can still use this given formula. So actually, the two have the same formula. They only differ in the value in which s is approaching 2. Okay, so that's for the initial and the final value theorem, which would be the last that I'm going to discuss here. This will just be polished when you go to your controls later on. Okay, now as an example, determine the initial value and the final value of this function. So, what does it say? It says that you have to evaluate the limit of the given y of s from s to s to equal to 0 rather, and to s equal to infinity. So if it's the initial value theorem, you will evaluate s times this as s approaches infinity. Anyway, if you notice, if you will multiply, because that's the procedure that you will do, if you will multiply this function by s, that eliminates the s in the denominator, right? So if that eliminates the s in the denominator, we'll take that out. You will be left with to substitute 0 for the s here to get the final value. So if this is 0, 0, 0, this would be a 6. 1 times 2 times 3, that would be a 6, and this would be a 2. 2 over 6 is 1/3. That's easy for the final value theorem, because the product of your s, this s, and your given function of s will be at all times not equal to infinity as long as you substitute a value for s here which is greater than 0. Now, the challenge is when you evaluate this same expression, when you substitute now infinity for the s. So, if you substitute infinity for the s, this will be infinity plus 2. So, that would be infinity. And this would also be infinity. Infinity over infinity is indeterminate, or cannot, it's not specified, the value is not specified. So, what will you do? You use L'Hopital's rule, or you use the technique you've learned in differential calculus, wherein you divide both the numerator and the denominator by the variable that appears in the denominator having the highest exponent. What do you mean by that, miss? You have to have this expanded into one third-degree polynomial, and since the variable which has the highest exponent is s cubed, you will divide this particular expanded third-degree polynomial by s cubed. The same thing with what you have in here in the numerator. As a result, you will have an answer which will be not indeterminate anymore. Because whenever you substitute s to the remaining expression, that will not be anymore indeterminate. So in this case, your y of 0 will be equal to 0. Now, what is good about differential equations is it allows you to review the things that you have learned in algebra, in calculus, and differential and integral calculus, and even the techniques before that you have learned in calculus in terms of converting hyperbolic functions to exponential functions, discussed already during our class then. Okay, so this is it. Please study on the conversion of indeterminate forms into something that is determinate. It actually, you did not study, but you only review because it was already discussed in your differential calculus. As for final value theorem, there's no worry because all you have to do is just substitute 0 for the s. Okay, so this ends their differential equation for this semester. Hopefully you have learned a lot, and what you have learned here actually you're going to still apply later on, especially with the CHE. I'm speaking of the CHE because differential equation has a lot of applications in kinetics and in process control, specifically the method of Laplace transformation. Thank you for listening, class.